Hey guys, I'm trying to do you a favor by taking what was two screencasts and condensing them down to one to try to save you some time. So you're welcome. All right, let's get on it. Plate tectonics is a lot of material. I'm going to move pretty fast. So when we look at the surface of the Earth, what we find is the crust or the outer part of the Earth is broken into 14 segments, kind of like puzzle pieces, or like if you crack a boiled egg, you've got these regions that are unbroken, and then there's these edges in between them. So these plates have these boundaries between them, and it's on these boundaries where all of the world's earthquakes and volcanoes occur. And the interior of these plates tend to be very quiet areas where not much is going on. And so our lesson today is try to understand what's up with this. In order to do that, we got to understand a little bit about the interior structure of the Earth. So basically, the Earth consists of four basic layers. We have the very, very hot inner core surrounded by the liquid outer core. Then the bulk of the Earth is this thing called the mantle, and there's this very, very thin outer part called the crust or lithosphere. Now let's just dive in a little bit on these. Okay, so the core of the Earth is basically consists of mostly iron and nickel, kind of like meteorites. It also contains some heavy metals like uranium and things like that. And because of this, these heavy elements are undergoing radioactive decay, and that causes the interior to be very hot. I mean, if you could see the core of the Earth, it would be whiter or brighter than the surface of the sun because it's so hot. It's 6,000 degrees. Now, the inner core is solid, but the outer core, because the pressure is a little bit lower, is liquid. And that liquid iron spins and swirls as it does so because the world's rotating. And as it does that, that generates Earth's magnetic field. I don't know if they'd ever ask you that question, but Earth's magnetic field, which protects us from a lot of solar radiation, is generated by these swirling eddies in the outer core. Now, the mantle is what's really important to this lesson. The mantle is the bulk of the world's volume. It consists of this semi-solid, semi-liquid material that's chemically, its composition is very similar to seafloor material, the volcanic activity you find in the middle of the ocean. But it acts like almost like cement or toothpaste. It can move really slowly, and it does. So it's not like a liquid that flows quick, and it's not like a solid that doesn't move, but just it goes along very slowly, and that's going to be really important to understand what's going on with plate tectonics. Now let's just talk about the crust real briefly. The crust of the Earth is the sort of the brittle out part of the Earth, the outside surface of the Earth, very, very thin. So like, for instance, it's about 10 kilometers thick in the oceans. It's considerably thicker in the continents, maybe like 80, 60 to 80 kilometers thick. And often, instead of talking about the crust, we talk about the lithosphere. So the lithosphere is the brittle part of the Earth, which consists of the crust and the uppermost part of the mantle where it starts to act like a solid. Okay, so you might hear me use both terms. I'll try to use the word crust mostly. All right, let's get on it. Convection is an important idea in this unit that we're doing, this Unit 4 unit, and it comes up right now with plate tectonics. So convection basically means this. When I heat a fluid, a liquid or a gas, what happens is the atoms vibrate more violently and they get space between them, and that makes them less dense, so they float upwards. Then they lose their energy and they snuggle back together, they become more dense and they sink back down. So we find is where heating occurs, you get this upward movement of hot material which cools off and then sinks back down, forming a thing called a convection current. And the reason that's important is in the mantle, we have these convection currents. So it's hot at the outer core and cold at the surface. So what happens is we get this upward movement of mantle material, just like we did in the last diagram. It cools off and then it sinks back down. And the thing is, because the mantle is the majority of the world's volume, and because it's very thick, and because the crust is very thin, it is able to drag the crust along with it as it moves. So the movement of these tectonic plates and all the earthquakes and volcanoes associated with that are basically being caused by the motions of these convection currents in the Earth's mantle. Now, where these convection currents come up, they come up like this, right? And so the rising material moves off in this direction, it moves off in this direction, and it drags part of the Earth's surface this way and part of the crust that way, and cause it to split apart. And when it does, magma is going to come up and take its place. So there's going to be volcanic activity here and some earthquake here. We call this a divergent boundary. It's diverging from each other because as this mantle material comes up in this convection current, it pulls one way and one the other, so they diverge from each other. We also call this a spreading center because the seafloor is spreading apart there. We mostly find these in the middle of the oceans, as we'll see in just a minute. So there's Mostly when we talk about spreading centers or divergent boundaries, we're talking about a thing called the mid-ocean ridge. When we look at the oceans, they're mostly these very flat, long, wide open places called the abyssal plain. But then there's these mountain chains, these very, very long mountain chains called mid-ocean ridges. And they're not necessarily always in the middle. They are in the Atlantic, but in other oceans, they're not in the middle. But we call them mid-ocean ridges. And what we find in the mid-ocean ridges is constant, very gentle, mild volcanic activity and very gentle, shallow earthquake activity. And what we find is on one side of the mid-ocean ridge, the ocean floor is moving this way, and on the other side is moving the opposite direction. Again, because the mantle is doing this. Now, another place we find this is in the rift valleys of East Africa, Kenya, Lake Victoria, that area. And basically, what that is it's just a new ocean basin forming. So basically, a convection current has come up underneath a thicker continental material and is starting to fracture it and pull it apart. So Mount Kilimanjaro that you've heard of, it's some of the volcanic activity associated with this Rift Valley system. And in time, the eastern part of Africa is going to be a small continental landmass, and there'll be a body of water between it and what is now the western part of Africa. Now, here's a nice little GIF that's showing us what's going on. So the mantle is coming up going this way. Is this convection is coming up going this way? This side of the lithosphere is being pulled this way. This side is being pulled that way. And as it does, you can see magma comes up and we see it freeze and then it moves away. And it moves away at about 5 centimeters a year. That's about the rate at which this tectonic motion is occurring. But the world's very old, and so even though 5 centimeters a year seems very slow, given enough time, it can make big changes. Like, if you went back to the time of the dinosaurs, turns out the Atlantic Ocean didn't even exist. It was like rift valleys that we see in Africa right now. But here's something that's important: is that the youngest material is in the middle, and the farther I get from the mid-ocean ridge, the older the seafloor is going to be. This maybe shows it a little bit better. So remember is the convection is moving one side to the right and the other side to the left because the convection currents underneath it in the mantle. As this comes up, this dark rock right here represents brand new rock. It's 1 million years old. Okay. As time goes by, 5 centimeters a year, now here's that same material, and 1 million years have gone by, and new material has come up at the mid ocean ridge. And still, this is moving this way, and this is moving this way. They used to be together, but 1 million years later, one part of it's here, one part of it's here. And as time goes by, now it's 2 million years away, 2 million years old. So it's even farther. And as time goes by, this material, which started at the middle trench, is going to get farther and farther and farther away. Now, this diagram showing anything about magnetic polarity we're not going to get into. So these divergent boundaries have some characteristics that we should know. First of all, there is very frequent, very gentle volcanic activity. Basically, volcanoes are only violent when they have a high water content because water makes steam and steam makes explosions. But this material is coming up from deep in the mantle where there isn't any water, so there isn't anything to make explosive pressure. So these volcanoes tend to be uh, very mild. All right. And when I pull the rock this way, it's kind of like cracking my knuckle. I don't know if you hear that. All right. It's not, it's pulling apart doesn't make big forces. So you don't build up a lot of energy to make big earthquakes. That happens when you squeeze things together, right? But when you pull them apart, not so much. So what we find here is gentle volcanic activities, gentle, shallow earthquakes. That's what we associate with these divergent plate boundaries, which are usually mid ocean ridges, but can also be African rift valleys. Here's a map that shows it quite well. This is an earthquake map of the North Atlantic, and you can see the mid ocean ridge running here, right? So, so it's just this line of volcanoes and volcanic vents and gentle earthquakes. Here's an earthquake map of East Africa, and you can see most of the earthquakes are happening here in the interior. There's not a whole lot going on, and if you notice here, the was that the Red Sea and the Gulf of I forget, but basically, I'm not very good at geography. But that used to be connected to Africa, and about 10 million years ago, this rifting happened there and it started pulling it apart. Okay, so these are called divergent plate boundaries. Now, thing is, if I'm making more Earth's surface in one place, I got to be getting rid of it somewhere else because the world can't get bigger. It's got a finite volume. So what happens is, just as new material came to the surface where the upwelling brought mantle material up, where that mantle material cools and sinks back into the mantle towards the core, it's going to drag that material back down with it. So old seafloor material gets dragged down into the mantle where these convection currents sink back in. All right. And these places where it sink back in are called ocean trenches. So most of the seafloor consists of a thing called the abyssal plain. It's about 5,000 meters deep. But it was kind of strange when scientists started mapping out using sonar the ocean floor. They found like these regions, these long, long regions. They go, we'll see in a second, they just go a long, long way, thousands and thousands of kilometers, where all of a sudden it's super deep, like 11 kilometers deep, right? And basically, these trenches, which is what we see right here, they occur where the lithosphere is sinking back in. So basically, here I have convection sinking back in. It's carrying this ocean floor material with it, and where it does, we get these trenches. Now, here's a picture. So here's a trench in the Aleutian Islands. This is the Pacific Plate. Not much volcanic activity or earthquake activity here, but man, there's all kinds of volcanoes along here. There's Japan for you. You know they have a lot of earthquakes and volcanoes. So do the Aleutian Islands. They're all volcanoes there, and they're full of earthquakes. So that's because we have these deep trenches where basically the Pacific Plate is moving this way here, and it's sinking. Oops, and it's sinking underneath the Asian plate. And here it's moving this way and sinking, I think, still the Asian plate. Now, these we call these regions where the crust is sinking back down to the mantle at trenches. We call these things subduction zones. So think like a submarine is going under. Subduction zone. I'm not as going under and ducking under. Okay, subduction zones. They are associated with these ocean trenches and sinking mantle material. Okay, now what we associate with these is instead of just shallow earthquakes that are very gentle, like we get at divergent boundaries at spreading centers, here we get something very different because this is being crammed up against this. So we're pushing them together and we get very powerful earthquakes. The most powerful earthquakes in the world happen at these subduction zones, and they start at the surface, and they work their way all the way down to a depth of about 700 kilometers. And at that point, this rock material that's sinking finally completely melts away. It starts melting, I don't know, about 300 kilometers down, but then it completely melts away by the time it gets to about 700 kilometers. Now, we can have different types of subduction zones. Well, two types really, because you have to have an ocean trench to have subduction. All right, we can have ocean. That means we have ocean plate sinking underneath ocean plate. All right, and when that happens, we're going to get these deeper earthquakes. We're going to get volcanoes to form. But one thing to keep in mind is this rock here. It's this seafloor rock. It's penetrated by water. It's wet, and as it starts moving down, this wet rock starts to melt when it gets down about 300 kilometers. And at that point, it forms this very steam heavy magma that comes to surface and makes these really explosive volcanoes. So the most explosive volcanoes, Krakatoa, Pinatubo, Mount St. Helens, these are all associated with subduction zones. Now, an ocean subduction zone, since there's no land here to start with, what we find is on the side that is above the sinking part of the seafloor material, we'll get a series of islands that will exactly parallel the trench, but only maybe 200 to 300 kilometers inland from it, away from the ridge. And so there'll be this parallel line of islands. Look back here. See this? These islands go right along here. These islands all see how they just parallel the trenches. There's islands here too, and these are happening because this material is melting here. All right. But we can also get, at least in South America, off the coast of the west coast of South America, we have one where we have a trench over or next to a continental landmass, right, forming the Andes Mountains. So it's very similar in every way to the ocean one. We still get deeper earthquakes. They're very powerful. We have wet rocks, and when it melts, it makes very explosive volcanoes. The only difference is there was continent here, and that continent crumpled. And so we get these very tall mountains forming as a result of this compression. So we get these high folded mountains that also contain these very violent volcanoes and are also subject to these massive deep earthquakes. Oops, I just hit the button. Right. So here, this is a nice graph showing you the deeper earthquakes, the melting occurring here causing the volcanoes. Here's Japan. You can see as it more detail. Here's the trench, and you can see as this plate is pushed this way, as it sinks down, this point here is right beneath this here, and that's causing these volcanoes to form. Now, there's 14 of these plates. You don't need to know the names of them, but you do need to know a little bit about these boundaries, about the different types of boundaries between them. There's 14 of them. They're in constant motion. You do need to know that the interior of these plates tend to be free of earthquakes and volcanoes for the most part. Most of the world's earthquakes are going to happen. Most of these earthquakes and volcanoes are going to happen at these plate boundaries. So look at this. This is an earthquake map of the world. I can see this pattern right here. This pattern I can see right here. This is kind of cool here because we're color coding, so we can see like the earthquakes getting deeper as they move away from the trenches. So there's a trench here. We can see them getting deeper, deeper, deeper as they move away. Green being the deepest earthquakes, red being the most shallow ones. And we see that there's very shallow earthquakes out here in the spreading centers of the mid-ocean ridges. If I look at a volcano map of the world, I see pretty much the same thing. Now, this is not listing um, the type of volcanism we see in these volcanic vents of the mid-ocean ridges. It's just actual volcanic mountains. But if you look at where the world's volcanic mountains are, the vast majority of them are located along these plate boundaries, especially around the Pacific plate, because this is the most active. This mid-ocean ridge here is very, very active, and so it's driving the subduction very furiously, and that's why this is often referred to as the Ring of Fire. Just because this is the world's most active mid-ocean ridge, it's causing seafloor spreading to happen at a faster rate than other places, so it's causing subduction to happen at a faster rate, which makes for more violent earthquakes and makes for more frequent volcanic activity. So there's three different types of plate boundaries the College Board wants you to be aware of. There's only three that exist, but they want you to be aware of them. And they are divergent, they're moving away from each other. There's convergent, they're being pushed towards each other. And then there's transform, they're sliding past each other. And let's just look at each of these in turn. I don't know why that's there, I hate that. Okay. So a divergent plate boundary, you have basically a seafloor spreading. It's where the mantle materials reach the surface, and one side is being dragged one way, one is being dragged the other way. So we associate these with mid-ocean ridges and rift valleys in Africa. We associate these with mild volcanic venting and shallow, frequent but low magnitude earthquakes. Convergent boundaries are a different matter. The convergent boundaries we associate with very powerful earthquakes that can extend from the surface down to depths of 700 kilometers. We associate them with violent volcanic activity because there's a lot of water in the magma that's associated with these. Now, there's three types of convergent boundaries. I can have ocean, so the trench is just in the middle of the ocean, like Japan or the Aleutian Islands. I can have ocean continent, where I have seafloor, like the Pacific plate is going, actually the Nazca plate is going underneath South America, which is a continent, but I still have a trench. And I still have volcanoes and everything else. And then I can have, in one case at least, there is continent. And basically what happens is the Himalayan mountains are the example, this famous example. We don't get volcanoes here because nothing is being subducted anymore. There used to be subduction. So imagine if right over here there was a landmass and it was coming this way. And basically what happened is we basically subducted this ocean away. And then the two landmasses are being crammed up against each other. That's continent. You get lots of powerful earthquakes, but you get folded mountains, but you don't get any volcanoes because we're not sinking things deep enough into the mantle to cause them to melt and form new magma. And finally, we have transform boundaries. There's only really one famous transform boundary, and that's the San Andreas Fault of California. But it's pretty impressive. It basically extends from the Sea of Cortez all the way up through California. It comes out just north of San Francisco at a place called Point Reyes. If you end up going to school in California, you got to check this out. It's pretty wild. And basically, here you have the North American plate is moving to the southeast. And we have, I believe, I forget which plate this is. This is the Nazca plate. I don't think it's the Pacific plate. But anyway, it's moving in the opposite direction. So they're sliding past each other. Since they're sliding past each other, there's no subduction. Since there's no subduction, there's no trench, there's nothing going into the mantle. It's not a place where we have sinking convection currents. We just have these two things sliding past each other. So we're going to get a lot of pressure. We're going to get a lot of earthquakes, powerful earthquakes. But we're not going to get deep earthquakes because there's nothing sinking down into the mantle. So the earthquakes are shallow, but they're powerful. That's a bad combination. Powerful earthquakes near the surface. No wonder California has some bad earthquakes. And also, too, we don't find any volcanism associated with it because we're not pushing things down at the mantle where they're going to melt. Now we got hotspots, and I got to tell you, College Board asked about hotspots, and why don't they? Hotspots are cool. So the most famous one of all is Hawaii, okay? And so the idea is there are certain places, maybe like 10 of them in the world, inside the Earth, where you have these plumes, like very narrow focused plumes of very, very hot material. So for some reason, there's like a lot of radioactive decay happening in one part of the core, and it's really heating it up, and it's just rising, and it's just basically coming up so hard and fast, it just pokes out holes, boop, 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 and makes these volcanoes. It just pushes right through the crust, whether it's continental crust or oceanic crust, pokes right through it. And so this hot spot down where I have a hot spot down here, this rapid convection comes up and it pushes up and it makes a volcano. Mauna Loa, Kilauea, and there's a new one forming off the coast here. But here's what's wild. These hot spots remain stationary. They don't move. They're associated with this point deep, deep, deep in the earth. But the plates above are in motion, right? So I have this Pacific plate being dragged off in this direction. So what happens is when this one forms, it gets dragged away, and like 1.5 million years later, it's now here. Maui used to be here, and it was active volcanism, but the motions of the Pacific plate carried it away, and now it's over here. And if I keep going away, I get all the way over here to Kauai, and it's like 5 million years old. That means 5 million years ago, it was the new island, and then 5 million years later, it gets carried away. So it's kind of a cool thing. It's like this. It shows sort of the conveyor belt aspect of plate tectonics moving the Pacific plate. So here's a map showing the Hawaiian Islands. So we see the big island of Hawaii is basically the oldest rocks we find there, about 400,000 years old. We go to Maui, about 1.3, Molokai 1.8, Oahu 3 million rather, Kauai over 5 million years old. So and there's a new volcano forming here because the Pacific plate is moving this way, and it's going to carry the Big Island off of this hotspot, and all the volcanoes here will go extinct, and a new island is going to form over that hotspot. And there's a number of these hotspots, like the Galapagos Islands. Yes, that's a hotspot. The Canary Islands. One on the continent that this has formed is kind of interesting. Is Yellowstone National Park is an example of one of these. And it has had some violent activity in the past, though. Anyway, I believe. Oh, one last thing is just the symbols that we use. So the symbols that we use, and you'll see this on diagrams from College Board. Divergent plate boundaries, we use these parallel lines. Convergent plate boundaries, we use the sawtooth pattern where the teeth point in the direction of subduction. So we're saying like this plate is moving in this direction, okay? And then transform plate boundaries, we see this sort of side by side symbol. Thanks for watching. I know there's a lot of material to digest, but we just got to keep powering through this curriculum because the end of the year is coming up fast, guys. Okay, I appreciate you watching this. Take care.